And we're going to talk about representations of reactions here. So we can represent reactions in different ways. I think you guys are getting comfortable with the reactions as far as balanced chemical equations are concerned. This section here is known as your coefficients. I think you guys are fairly versed in that. Oops, why is this not, my pen's not working. Oh, great. One more thing not working. So I think you're fairly versed in this being a coefficient. This is called a formula unit. This is the state of matter. Do not put precipitate here. It would be a solid. Okay. Some people put PPT. Don't do that. This is a liquid, and then of course this would be a gas. These are your subscripts. I think you guys are fairly comfortable with these. We can also use these particulate diagrams to show the same thing. Here you can see that this is a solid, this is a liquid. You can kind of see the difference, but not real well between these two in this particular diagram. And then this would be a gas. You can tell that definitely because there's gaps, there's space between here. So I think that helps. All right, relative locations, important parts of those representations. State of matter. Again, your solid particles are going to be close contact. A lot of times they'll be in some sort of crystalline fashion to kind of show that that it's structured a little bit more than just a gas would be. Liquid particles are going to be close together, but kind of disordered, and they might be able to show some sort of movement going on there, but the majority of them have some attractions and repulsions that exist. Again, gas particles are going to be spread out as far as they can, and then aqueous, you're going to, a lot of times they will show just the solute particles, the ions that are disassociated, and leave the water particles out. If they do have water particles, those will or should be oriented properly so that the dipoles are the correct direction. So the hydrogens will be attracted, the hydrogen end of the water will be attracted to the negative ion, and then the oxygen end of the water will be attracted to the positive ion. And then you also have to consider, will the thing actually ionize? Will it break up into ions, or is it going to stay as a solid? And we'll get into a little bit more of being able to determine that based on numbers as we move through the year. Okay. All right. So here's kind of an example of the difference between solids, liquids, and gases. Again, the particles are going to vibrate in their own spot. They're not going to move. You can see that there's quite a structure here as far as being, more organized. Here for the liquid, they're still touching, but there's a little bit of space in between, and they're more jumbled. It's more random. And then gases are farther apart. They're going to have more space in between them. And sometimes they'll even have, like in that, they'll have a way to kind of show that the, these things are moving. So they'll have kind of an arrow coming out, or like we saw in one of the previous here, you can kind of see on here where they had like this, it kind of gives you the impression of motion. Okay. And then you could use context clues. So surface or interstices of alloys, you can see those. Precipitates, which are solid particles that would be at the bottom after they've settled. Interfaces where two different substances meet, like air and water. The amount, so proper number of atoms of each element given in a formula. And you guys kind of ran into that on some of your test questions, your multiple choice questions on your last test. Some of you are starting to come in and do corrections on those, and we're talking about those quite a bit during the corrections time. Use relative amounts of atoms when giving a quantity, so moles, concentration, coefficients, that sort of thing. And then make sure that you're observing the law of conservation of mass. There will be examples where that's not maintained, and those you would definitely want to reject as far as answers. As far as species, you would use, or they typically will use distinct shapes, symbols, colors, or shading to identify different ions or atoms. Ions, a lot of times they'll use the pluses or minuses to be able to convey that. Again, charges and align them properly. We talked about water just a minute ago, making sure that, you know, if you've got a water molecule, that you're properly aligning that with ions. We ran into a lot of that on the test, the last FRQ question from last unit. There were some issues with that. And then use appropriate sizing. So when you're talking about like different ions, for example, you know, did you draw the lithium ion smaller than the magnesium ion? Or the barium ion would be much larger. It's going to have a larger atomic radius. We talked about that. I believe unit 1 was where we discussed that. All right, so the I do portion here. We've got different, they wanted the formulas for the reactants. We have the reaction as H2 and Br2 react. This reaction does not go to completion. It's going to reach something called equilibrium. What are the formulas for the reactants? So what are they going to look like? What is the formula for the product? What is the balanced equation? What is the difference between pictures 2 and 3? And then what do you notice about the total atoms of the elements in all the pictures? What concept does that represent? So see if you can spend a minute doing that. And I'm going to try to spend a minute trying to get this pen thing hooked up so that I can properly answer this for you. Oh, there we go. Now it's writing. All right. All right. So what's the difference between 2 and 3? I would say that we've got that more of it's reacted in some more reactants. Or no, products, sorry, products. More products have formed. Okay. What did you notice about the total of each element in the pictures? The total atoms remain the same. And that is the concept of conservation of mass or matter, either one, has been maintained there. Okay. So here, when we're looking in picture 1, you can see that this is our H2. They give us a key down here. This is our Br2. It's diatomic. And then this is just reactants. Here, we're reacting, and we've got 4 molecules formed so far. And then here, we've now got 6 molecules formed. And then they said that it didn't go to completion. That means that we still have some of this present. Okay? Any questions on that? Yes, ma'am.
So how did you get HBr for formula?
Because hydrogen is a +1 and Br is a -1.
So what are the formulas for each reactant? There's H2 and Br?
Yeah. They gave you those right here. And they're diatomics, so that's why they're drawn together here and here. Yes, ma'am.
For the states of matter,
oh, did they say to do that? I'm sorry. Yeah, they're all this. I think this is a liquid because that's an acid, and I think it's big enough. It's heavy enough. I mean, HCl is going to be, that's liquid, that's hydrochloric. So HBr would be a liquid too. So sorry about that. Yeah, HBr is going to be a liquid. I can look it up real quick. Verify. State of matter, HBr. Oh no, a colorless gas. It dissolves in water, forming hydrobromic. Oh, okay. So it does forming hydrobromic acid. So if it's in water, it'll dissolve in water. So yeah, I guess it is a gas. Lippy has been corrected.
Is there a way for us to just like know that? Or
No. Yeah, no. No, and they wouldn't expect you to. It's fine. Actually, there is a way for you to know. You know how you would know? If they give you a diagram like this, do you see how the spacing's here? That's how we would know. Okay? All right. So that, ladies, did you hear me? How do we know that this is a gas? The diagram. Right. Okay. All right. So yes, there is a way to know. I had to think about it for a second. All right, so draw a representation, 4 molecules of hydrogen, 4 of oxygen, and have them forming water, which is a liquid at room temperature. Oh, Lippy, Lippy, Lippy Lou. Naughty Lippy.
That's what I did.
Don't be naughty like me. All right, better?
Yeah.
All right. So this is going to be our liquid, randomly placed, disorganized, but down at the bottom. And then we've got our two gases up here. Now, notice where it said 4 molecules of hydrogen and 4 of oxygen. Many, many, many of you on your FRQ last time did not read the numbers, and it told you how many of each thing to do. On the last problem on your FRQ, it told you so many of this or so many of that. So be careful with those and make sure that you're paying attention to when it gives you quantities. Okay? All right. Moving on. Physical and chemical changes then. Physical process, substance undergoes change in properties, but not a change in composition. We talked about this a little bit last week when we were discussing different phases and how we knew if it was actually a chemical change or a physical change. So here, same chemical composition, but the state of matter has changed from a solid to a liquid. So it's gone from ice to water here. Okay. Covalent bonds between hydrogen and oxygen are the same in both pictures. The density, though, is different. Okay. Solid ice is going to be more dense than liquid, which is kind of weird because most things, the solid form is more dense than the liquid form, but ice is one of those strange kind of things where that's not the case. But that's a physical property. Less dense. Yep, ice floats on the top because it's less dense. When mixtures are separated, you're going to use physical processes. It doesn't change them. The mixture separation techniques include distillation, filtration, and chromatography. We talked about those last unit. Mixture separated by a filter here is a physical change. You're just simply dividing these things out. They're not chemically bonded to one another. They're not touching one another. They're not chemically bonded. Chemical process, then, a substance is going to be changed into a new substance with a different composition. During a chemical process, the bonds are broken and new bonds are formed. So examples there would include chemical reactions, 2 elements bond together to form something new. A compound is broken down, so this would be a synthesis reaction here that they're talking about. This would be a decomposition reaction. Or you could have a neutralization reaction where water's formed. You could have double replacement, single replacement. So there's lots of options there. The bonds between the atoms are separated and new bonds are forming. The intramolecular, intra means covalent or ionic bonds. Those forces are broken and reformed. And we're actually going to be doing mathematical calculations related to this coming up. Okay, so how much energy is given off or how much energy is brought in if it's endothermic. So here you would have, whatever this is, it's getting rearranged. These things do not look like these things. Some cases, an argument can be made that a physical process involves a chemical change, such as salt in water is one of these. Okay, we're taking these ionic compounds. We are breaking those ionic bonds between those items, and they're coming off here in the water surrounding them. So there is kind of a debate in the chemistry community. Some people say this is a chemical change. Some people say it's a physical change. So it just depends on who you run into. I know that I've always classified it as physical just because it makes it easier, but just realize that there's a camp out there that says no. All right, physical or chemical here for the first one? Physical, because the chemical formula has not changed. We've just gone from a liquid to a gas, so this is going to be physical. Physical or chemical? Chemical, okay. Oh, and it also said what type of forces are going to be broken or formed. This would just be intermolecular. I'm going to do that, okay. I'm going to do that as that one. So this would be Ra, so intramolecular. Here, what is this? Intra, and it's chemical, and intramolecular, because I'm lazy. And what is this guy here? Physical, and that's going to be intermolecular. All right. So now you can do the we do option. Draw and label a diagram of liquid HCl becoming a gas. Explain how this is physical versus chemical. So what is changing? All right, so these intermolecular bonds here, I do it in my highlighter color. Those are going to be broken, but the intramolecular bond between the H and the Cl is maintained. And now it's in the gas form, so it's spread out from there. All right, makes sense? Questions about those? All right. So tonight's homework is 4, 3, and 4, 4. And then tomorrow is stoichiometry. BCA tables.